Welcome back to the shop. First off, let me kind of apologize to you for lying in the last video. I said that the next project we're going to be a dust tube for the Queen Bee Pro CNC that you can see here behind me. This video isn't that video. That project is still coming, but a bit later. Because I actually had a request for something I've been thinking about doing for quite a while. So the background is this. Most of you watching this are either in the process of building a homemade CNC like my Queen Bee Pro here, either from a kit or from scratch or from something in between. Or you are just generally interested in homemade electronics and mechanics and machine building in your garage. Now, I've gotten a lot of questions and requests about subjects that I didn't really cover in the Queen Bee Pro CNC series, and there is a reason I didn't cover it in that series. Like I said in the first episode, that series was more about actually documenting the build process of the kit and reviewing Bulkman as a supplier and the kit itself. But after reading all your comments and emailing back and forth with a couple of guys that watch the videos, I think there's actually a need or at least a wish for this content to be shown and explained. So that's why I'm launching this new series, which I'm going to call Machine Building Basics. And as the name suggests, I'm going to spend this series explaining how to build electromechanical machines in general, and of course, homemade CNC routers in particular. I already have around 7 subjects planned out, but if you have any ideas or suggestions, leave it down in the comments or send me an email. You will find the links to everything down in the description. So in this first video of the series, we're going to talk about switches. This is a limit switch, or to be more precise, it's a single pole double throw micro switch. This is the electrical equivalent of crossing 2 wires. It's one of the most common and cheap switches available. Chances are that you have a dozen of them around you right now without even knowing. But what did that whole single pole double throw thing mean? Well, let me show you on the bench. Here we have the same type of switch that I just showed you on the CNC. And single pole double throw means that it has one common terminal, or input if you want to call it that, and 2 outputs. Generally it's one normally open and one normally closed. And in case you don't know what that means that when we actuate the lever, the normally open leg is connected to the common, and the normally closed leg is not connected to common. And vice versa if we release it. Now the normally closed leg is connected to the common, and the normally open leg is not connected to the common. This is quite easy to illustrate. I have my multimeter in ohm range. Now this is a dirt cheap micro switch from China, so we still have some resistance on the normally closed input. Generally the resistance should be as low as possible. But if I actuate the lever, we have an open circuit. And if I switch leg to the normally open one, the reverse thing happens. It goes from open to closed. The benefits of these is that they are easy to use, cheap and abundant. And for the price you pay, they are also fairly accurate. They will actuate in the same point, plus or minus a couple of hundreds of millimeters every time. And for a limit switch, this will work just fine. Now, the main thing they suffer from is that this is a mechanical switch, and the mechanical components and contacts inside this will wear out over time, especially if they are breaking higher currents. Now, for sensing purposes, as for a limit switch, where we're only breaking a couple of milliamps, this doesn't really matter, so you can actuate it a couple of 100,000 times probably without ever having a problem. But if you're actually breaking a load of an amp or so, these will wear out quickly. This is the most basic component I'm going to show you today. So let's move one step up in the hierarchy. This is exactly the same thing as this, but more expensive. This is a piece of industrial Lego. You have 2 contact blocks, one normally closed, one normally open, and a button to actuate it. These are modular, meaning you can actually get any type of button you want for this. You can have a key, you can have red buttons, you can have lights in them, you can have turning switches, anything you want, and these are a staple in industry. These can break up to 400 volts, but generally they are used in 24 volt system for control purposes. And like I said, this is the same as this, and this is of course a non-latching button, meaning the contact will break when you release it. This is a single pole, single throw button with a latch. You have a contact, you make a contact, you release the contact. Simple as that. These aren't used for limit switches, but for off and on control. Now, this little bugger right here is kind of the same as this contact block on its own, with one important difference. This normally open contact is mechanically actuated. This one isn't. This is what's called a reed switch. Inside this plastic tube are 2 incredibly thin and lightweight metallic reeds, and they close when they are in proximity of a magnetic field. So allow me to demonstrate. This is a neodymium magnet, and I'm not making contact between the reeds with the metal cover, simply the magnet field. Now, this type of switch isn't that useful when building machines, because it is an excellent way to make a bad contact. What I mean by that is that they are really prone to contact bounce. Now, contact bounce isn't something you really have to worry about when building a homemade CNC machine, because the inputs in our controllers and breakout boards are either debounced in hardware or the debounced in software. Now, contact bounce happens right before a switch makes 100% solid contact. And that means that the signal on the output goes something like this. It goes from 0, we're starting to make contact, we've made full contact. And like I said, this can either be handled in software or hardware. In software you have a filter that basically says, okay, ignore anything that is faster than this time. Or in hardware you can use something called a Schmitt trigger that only gives a solid 0 or a solid 1. Or 0 volts or 5 volts or 10 volts or 24 volts or whatever your control system uses. And the rest of the switches here have it implemented in hardware already. But if you're building another type of system using an Arduino or Raspberry Pi or some other type of microcontroller and you want to know how to handle this problem, tell me down in the comments and I'll make sure to cover that in an upcoming video. Now, let's move on. This switch is almost the same as this switch, but not quite. This switch contains a Hall effect sensor, and the Hall effect sensor does the same thing as the reed switch. It activates when in the presence of a strong magnetic field. However, it doesn't do it mechanically as the reed switch does, with two reeds that connect. It senses the magnetism, and then a transistor makes the closed circuit. Let me demonstrate. Now I'm all hooked up. This electronic switch has 3 inputs. It has the positive power, which can be between 12 to 24 volt on this model. We have the ground, and the signal output is connected to the V input on my multimeter right now. And as you can see, the magnetic field actuates the switch and gives a signal on the output wire. Now, this model of switch in particular is made for pneumatic cylinders. So this small sensor fits in a slot on a pneumatic cylinder and acts as an end-stop switch or end-stop limit switch. You can also find these on some old CNC machines. Then you usually have a magnet embedded in either the bed of a lathe or the column of a mill, and the reed switch in the corresponding part that moves back and forth. Now, both this switch, or sensor, and the rest of the sensors I'm going to talk about, have a couple of really big advantages over the mechanical micro switch. Now, the first one is that they are completely sealed, so they are extremely resistant to any type of harsh environment, such as cutting oil, dust, or chips from a milling machine. Whereas this one can close a couple of 100,000 cycles without breaking. This one can be actuated several million times without ever failing. It also has the advantage of being non-touching, which of course saves on wear and tear. And because of this, it is of course quite a bit more expensive than this one. And for our main component of this video, I give you the inductive sensor. Now, these are a staple in any industry and in any machine you have probably ever laid your eyes on. They are abundant and used everywhere. This is exactly as the Hall effect sensor, an electronic switch. This is a 4-pole model, meaning it has both a normally closed and a normally open output, the same as the micro switch. This one is only normally closed. These two have different sensing ranges. This one has a sensing range of around 12 millimeters. This small one, or thinner one, has around 8 millimeters. Now, you can get bigger inductive sensor that can sense objects up to around 30 millimeters or so. They are very precise and very sturdy. When used as limit switches, they will actuate in the same point in space every single time, down to more or less 1/100th of a millimeter. And this makes them extremely useful. The main difference between the inductive sensor and the Hall effect sensor is that this one doesn't react to magnetism. It reacts to metal. And on the plus side, it reacts to any type of metal. Both non-magnetic, like this piece of aluminium, or stainless, or even brass. And this is of course extremely useful. This also has the same advantage as the Hall effect sensor of being extremely resistant to harsh environments, such as oil, moisture, cutting fluids, and chips and other mechanical abrasions. The only thing that it's kind of sensitive to is any type of metallic dust or chips, because if this surface gets caked, then this of course will actuate all the time. So you do need to keep the face clean to make them working properly. That being said, I have seen sensors exactly like this one, buried in mounds of fat and dirt and grease and oil and metallic chips, and still work perfectly fine. They are of course also more expensive than the micro switch, but also a hell of a lot more useful. The way these work is that in the front here is a metallic coil, and coils have something called inductance. Now, I won't explain what inductance is, but you can look it up if you want to. The main thing you need to know is that we can measure inductance. And inductance changes when the coil is in the presence of You guessed it, a metallic object. And this is why it works on both magnetic and non-magnetic materials. But it has to be metallic, it has to be conducting electricity for this to work. And the electronics inside this switch senses the changing inductance in the coil and then closes a transistor on the output side, or opens it if it's connected as a normally closed switch. Now, most of the inductive sensors I've worked with will work with an input of between 12 and around 36 volt DC. Right now I'm feeding around 13 volts into this one, and as you can see there is a slight drop to the output side. It's 12.7 volts or thereabouts. Now, generally in industry they are used with 24 volt systems. Now, there are some models like this one that is meant to be used with a 3D printer, and it should work down to around 5 volts. I haven't checked that actually because I haven't had need for it, but they do exist. And you can be sure that when I upgrade my Queen Bee Pro CNC to a 24 volt electrical system, I'm definitely going to use inductive sensors for all the limit switches. Inductive sensors, or any type of electronic switch really, comes in two varieties, PNP or NPN. These are also called sink or source. And it's important for you to know the difference between these ones, because not all controller boards or breakout boards can work with both types. They generally either work with NPN sensors or PNP sensors, so make sure you buy the right kind. PNP sensors, such as I have here, are sourcing components, meaning that when you close the circuit or activate the sensor, they will source current on the signal wire. So as you can see, this one gives 12 volts on the output wire. NPN sensors, on the other hand, they will not source current, they will sink current, meaning that when you activate the sensor, the output will be pulled down to ground. And these switches are just as good as the ones I have here and just as useful, but like I said, you will need to make sure that they work with your type of breakout board. And as far as I know, almost all breakout boards work with PNP sensors, so keep that in mind when you order your components. There is also one more type of electronic sensor or switch that is really common within industry. Unfortunately, I don't have one here to show you, but on the outside, they look really similar to inductive sensors, with the main difference that they are capacitive instead of inductive. They share basically all traits with the inductive sensor, of the sensing distance, of them being resistant to harsh environments, of the output types, of the PNP or NPN types. But the main difference is that they aren't only activated by metallic materials. They are also activated by non-conducting materials such as plastic and wood. And this is of course useful when you don't have any metal to actuate on. Now, like I said, I don't have one of these sensors to show you, but to be fair, it's not that likely that you're going to use a capacitive sensor in your home-built machine. And with that, I think I've talked long enough on this subject, and you should be able to use any of these components I've showed you effectively in your project, no matter if it's a home-built CNC router or other type of electromechanical contraption. Now, if you're building something cool where you can use any of this knowledge, I would love for you to share it with me. So send me an email, leave a comment, link to it any way you see fit. I'd love to check it out. And as always guys, if you like what you're seeing, you know what to do. Till next time.